Hi, I'm Charles Lesire. I'm a senior researcher at Onera in Toulouse, France, and I will present a work I've done with my colleagues David Dawes and Christophe Grand on the formalization of robot skills with descriptive and operational models. Let's consider that we have a drone and that we have developed and programmed a lot of algorithms within this drone, like control algorithms, waypoint navigation, or the detection and tracking of people using the camera, for instance. And to do so we have designed and coded a lot of algorithms in the system, for example, using some quite standard middlewares like IROS or ROS2. And at the end, we have a very complex software architecture with a lot of nodes and a lot of links between these nodes. Now we would like to give the drone to a user and have the user perform more operational missions. For example, we would like to use the drone to inspect the infrastructure of a bridge, for instance, to detect anomalies, or to be able to follow a boat in a convoy in order to detect some threats or attacks on this boat. To perform this kind of mission, we cannot just give the drone and all the ROS architecture to the user and expect the user to understand everything and be able to program the drone. What we want to do is to have some kind of intuitive and easy way to program a mission of the drone without knowing all the details of the ROS architecture. Moreover, we would like to give some guarantees or check some properties on the behavior of the drone so that we can get some approval or even a certification from some authorities. To do so, we need to implement several things for the functional layer of the system architecture or for the mission programming or for the verification. What we propose is to organize the software architecture into functions or skills so that we can define some high-level functionalities that we provide. And when we define these skills, we will have to describe the constraints for the skill execution, like the fact that a skill depends on the availability of a sensor, or that two skills cannot be executed at the same time on the system. We also want to provide a standard interface to give a common way to invoke the several skills execution. Or even we could propose some skill models describing how the skill will behave and be executed. On the mission programming part, we would like to be able to program the mission by combining the several skills of the drone based on their inputs and outputs, so that we could, for example, have simple instruction like sequences of skills, parallelism, management of several skills, and their failure modes, for instance. We will also like to use some more modern programming environments that use formal models like behavior trees, Petri nets, or state machines. And to do so, we need to have formal models of the skills themselves. And finally, we will also like to use some automated planning techniques to be able to automatically build the mission program. And we need some models like PDL models for automated planning. Regarding verification, we would like to provide some guarantees on the behavior of the drone, depending on the mission it has to perform. And we will use some model checking techniques to perform this verification. And these techniques, again, use formal models of the system. To develop and deploy all the process I have detailed on the system, we have to face a quite important challenge, which is to ensure the consistency between all the models. So we have some models of the skills on the functional layer and the links between the skills and some other functions of the system, some nodes of the architecture, some sensors, resource modes, for instance. We have some models for mission programming like state machine or Petri nets or behavior trees. And we have some models for verification like state machine models again, or PDL models for automated reasoning. And the challenge here is to ensure the consistency between these models, because when we provide some guarantees on the system behavior, we have somehow to be confident that the system that will be deployed is consistent with the models that we have verified. Also, we would like to provide some tools to support all the steps, so not just to provide models, but also to provide some practical tools to help the programming of the skills within the functional layer, to help mission programming, and to make an interface with common tools for automated reasoning. What we propose in this work then is to have a language, to design a language to describe skill models. And these skill models will be central models that we will be able to use in the functional layer to develop skills, in the mission programming to program missions, and in the verification part to check properties. Based on these skill models, we provide some tools, and these tools will allow first to generate some IROS nodes to be able to manage skill execution within the functional layer in link with the software architecture you have developed so far. We will provide an interface library to be able to use the skills and have a quite easy way to start the skill and get some status of execution of the skills. And finally, we provide some model-to-model translation tools to be able to derive from these skill models some more specific models like PDDL models for automated reasoning or state machine models for verification. Now we'll go a bit deeper in the specification language for the skills. So we consider that the functional layer of our system provides some skills, and these skills are organized into skill sets. If you have a quite simple drone, you can consider that you have a unique skill set corresponding to all the skills of your drone, or you can split these skills into several skill sets depending on the categories you have defined. So for example, you can have a guidance skill set containing skills related to the guidance of the drone and some image processing skill set related to image processing skills. Within the skill set, you can define data, so some data that are provided by your robot. You can describe some functions, so you can describe some functions that model parts of the system, like the effect of an action or conditions on an action, for example. We'll see an example just after. You have to define some resources. So resources can either reflect the state of something in your system, like the state of a driver, the fact that the driver is on or off or is broken, for example. Or you can use resources to describe conditions or constraints between the skills, like the fact that two skills cannot be executed at the same time. Resources will be modeled using state machines. And finally, you will define all the skills of your skill set. A skill is defined by some inputs, so the parameters needed to execute the skill. A precondition describing the logical situation in which you will be able to execute the skill. And the list of needed resources to execute the skill. So for each resource, you will describe some constraints on the state in which the resource must be to execute the skill. And you will also define some terminal modes for the skill. So that are all the possible states in which the skill will end its execution. So typically we have a nominal mode corresponding to the fact that the skill has achieved the goal that you asked it to do. Or you have some failure modes or some side effect modes, for example. And you will also define a progress period at which the skill will report the progress of the execution. You can find the full language grammar described on the Robot Skills website on gitlab.io. In this website, we also provide some tutorials to understand the skills language and use the tools we provide. And we have based this tutorial on the TurtleSim tutorial. And so in this slide, we see, for example, the model of the skills available on the TurtleSim simulator. So we have defined a unique skill set for the TurtleSim, and in this skill set we will provide the data, the position of the turtle. We will provide a function, isSafe, that will help to determine if a position is safe, so it means that it's in the boundaries of the simulator. And then we have defined a resource. This resource gives the status of the simulator, which could be unavailable or available. Unavailable means that the simulator has not been launched and we cannot ask him to move or act on the turtle. As you can see, these transitions on these resources are tagged as extern. It means that the skills of the model cannot control the transitions. The transitions can only be controlled from your functional architecture, so from the nodes that you have developed in your software architecture. Then we define the skill, teleport, and this skill will teleport the turtle at a given position. So it takes as input the target positions at which you want to teleport the turtle. And it defines some constraints on the resource simulator. So this skill can only be executed if the simulator is available and stays available all along the execution. This skill has two possible terminal modes: arrived, which is a nominal situation where the teleport has succeeded, and collision. If you consider that you have an obstacle in the simulator, you can collide with this obstacle when teleporting the turtle. In the tutorial, we also analyze some other skills like painting lines and things like that. Now we have defined the skill models, and we want to use these models at several steps of the process, like to execute the mission. So in mission programming part, it's operational models, and to reason about the skills and the system behavior in descriptive models. Regarding operational models, we propose an architecture to manage the skills execution. So this architecture is made of managers on the functional layer. So these managers will connect with the software architecture you have developed so far and provide a common way of managing the skill execution. This management of execution is accessible from the mission controllers, so the mission programming part, through a skill set interface. The managers that we propose consist in a data manager that will subscribe to internal data in your system and provide some getters to this data. A resource manager that will keep track of the resource states, and these states will evolve according to transition requests coming from the skills themselves or from external requests coming from your software architecture. And finally, we have some skill managers that will implement the skills in relation to the functional modules of your software architecture. We provide some tools to generate this manager in ROS and ROS2, has a unique package containing all the managers, where you can define some hooks to implement the link with your functional models. Regarding mission programming, we provide an interface library, which is a Python library that uses ROS in background to get access to the data and resources and to control the skill execution. The simple API does not need that the user understand ROS. You have a simple and abstract interface to use the skills. We have a more advanced interface that allows to include this interface library within Smash or behavior tree nodes. Here you have a very simple example of using the Python interface to use the skills provided by the turtle sim in order to draw a very nice figure. Regarding descriptive models, we provide some model-to-model translation tools towards some descriptive models, typically towards PDDL for automated planning. So we translate the skill models into PDDL models, and we also translate the skill models into state machine models that we have used to make some model checking using new SMB. We have made an application with this robot skills language and tools using a drone that performs a search and rescue mission after a disaster. We have developed all the skill managers within this drone to perform all the navigation and processing and mapping skills. We have then defined a very simple mission for the drone using Smash and the interface library. And we have defined a more complex mission using behavior trees where we manage some sensor failures and navigation failures of the drone. Finally, you can find all the language, the generators, and documentation in the tutorial on our website at gitlab.io. Thanks for listening, and if you have some questions, do not hesitate to contact me.